Everything works.
Dao Shenka. Good morning. Good morning, Beijing. It was a bit tricky technically, but we managed to do the transfer of slides. It's an honor to be here. It's an honor to be given the chance to give this opening keynote. Thank you so much for the organization. Thank you so much for welcoming us in Beijing. So 10 years ago, I was a young professor doing work on forecasting like many of you. And as Chris just reminded me just before, there was a controversial topic. You know, to improve my forecast, I wanted people to share data. And obviously, they didn't want to share data. So I would say push myself. I worked on the first paper where I said I'm going to propose a method where people can learn and do forecasting based on distributed data, but they will never share the data, right? So we're going to do distributed learning and forecasting with some kind of encryption layer. And 10 years ago, I wrote this paper and I had the chance to come present it at a conference. Do you know where the conference was? It was at the Friendship Hotel in Beijing, 10 years ago. So I'm very happy to be here again 10 years after to give a talk on the topic. Hopefully we have made some progress. So I want to inspire you. I want you to understand why I'm so obsessed with this question of data sharing. And especially I work on incentivizing this data sharing. So let's go. The agenda is that I want to give you an overview, context and motivation. I want to give you some kind of examples for what I mean by market-based analytics. We're going to have a market framework. Then I will introduce a specific market I've been working on, and that was published some years ago. And then I'll have some illustrations of simulation and case studies. We'll try to keep some time for questions at the end, obviously. So context and motivation. I work a lot with energy forecasting. I really like working with energy, but I also work with shipping. I also worked with weather forecasting. I've been doing some business analytics, etc. And if you were going broader here, not just looking at energy, but smart cities, industry, smart transport, smart agriculture, I think we can all say that we want to be smarter with data, right? And smarter is not just data, it's data and analytics. So many of us as forecasters, we're exactly there, right? We work with data, we do analytics, and we try to generate value for our users. So that can be forecasting for some business analytics, as I was saying, that can be for some critical infrastructure management. In all cases, you need data and analytics. So, where is this data coming from? A bit everywhere. I have to say, I have a huge respect for China. I think China has been so good at generating data over the last 10, 15 years. And yes, we need to generate data. Some companies have understood it very well. And The Economist had this nice visualization some time ago. I know that one of my students, Shiwen, will share a better visualization even in the coming days when she gives a talk. And this visualization is about these giant companies based in the US. That generate a lot of data and generate value from this data. I'm sure we could make the same peak with Chinese companies. They are very big, very large Chinese companies that generate a lot of value from data. Okay, but then when it comes to generating value from data, we've had different types of paradigms over the year. We first had an obsession with what we call big data, right? So today we still use big data as a term, but the way we focus on it is a bit different, right? It's technical, we just centralize a lot of data, we have big computers, we do our analytics. Yes, it's technical and large scale, but we know how to do it. We assume that the data can be centralized, we assume that we have these big computers. Then in parallel, there's edge computing. Right? Some people have realized it doesn't make sense, maybe to always want to centralize the data. So we should do some computation centrally, and we should keep some computation at the edge, right? And that's edge computing. There's been a lot of work on these two topics over the last 20, 30 years, but in all cases, there's an assumption is that people will share data, being by centralizing the data, or even by working at the edge. The data ownership is distributed. We all own data. You own data. Companies own data. That doesn't mean you want to share it. That also doesn't mean you know how to share it, by the way. So we have made an assumption, and it's a gap now. How are we going to be able to have an ecosystem where a lot of data is generated, but the ownership is distributed, and the way to generate value is by getting this data to flow? We're working on a very large initiative at Imperial College that I hope will become real at the end of the year. It's called the economics of AI. We want to look at AI data as an ecosystem where we think about all these users, all these agents that generate data, and how we can somehow make this ecosystem work optimally for society, for industry, etc. So how are we going to do that? We're going to develop some collaborative and market-based analytics. You will understand what I mean with that. Good. So what is market-based analytics? I have an example. As I said, I'm an energy forecaster, and some of the reason why people know my work is there's been very strong application in trading, energy trading. So an example for energy trading with wind farms. I was living in Denmark, so there's a strong focus on wind energy. This is that you would have a bunch of wind farms, like here, 3 wind farms for instance. When they go to the electricity market, they place an offer in advance. To place this offer, since it's in advance, they need a forecast, a weather forecast that becomes a wind power forecast that becomes a bid in the market. The market is such that any forecast error costs you money. You have a loss of revenue because of forecasting error, right? All these people know it. The operator of wind farm A, the operator of wind farm B, the operator of wind farm C, they all know any forecast error is going to cost me money. So you have a strong incentive to improve your forecast. Beautifully enough, if they could share data, they would improve their forecast, right? You can show that. You can do a lot of experimental studies. You can develop new methods even to do better and better and better. But in practice, they have no interest in sharing their data. They think they're going to lose a competitive advantage. They think they're going to lose money even, right? So they don't want to do it. How can we design a framework so that they are incentivized and rightly incentivized to do so, right? So that's been my endeavor for the last 10 years. This first paper I was mentioning, I presented here, there was no money involved. I just thought, okay, we can do some collaborative analytics. People are just going to work together. They don't share the data, but they still help each other through some kind of distributed computing. Maybe it's a bit naive, maybe it's not. But now we're trying to put some incentive in the game, so that's why we consider both this market and the collaborative analytics. I mentioned energy, but it's not just about energy. If my only application area was energy, I think it would be a bit limited, a bit lame even. We've seen since then that there are lots of other application areas of relevance and very, very fun, actually, impact cases. If you think of business analytics, one story I've been telling, so I thought of it actually when I came to Hong Kong for the ISF a long time ago. Hong Kong is big on tourism and hospitality, right? Forecasting and analytics for tourism and hospitality. There's no data sharing between airline company, hotels, all the shops there. But if you want to do demand forecasting for all the tourism and hospitality related activities, it would be so nice that there's some data sharing, right? That we collaborate based on all this distributed data. So this is a very nice case in terms of business analytics. And we know this has been done in supply chain management, for instance. You know, along the supply chain, already in the 1980s, some people were saying, how do we optimally collaborate? How do we get the data or the relevant information to go upstream and downstream? If you think of it, smart mobility, congestion management and routing is also a case where you have a lot of distributed data and there's a strong incentive for data sharing, right? It's already happening if you think of Google Map, Waze, etc. But we don't have some general purpose approach, a platform for data sharing. It's just specific companies that found a way to make it work. Then in energy, we have a lot of case studies. And eventually with IoT, if you think of IoT more generally, we can see also a lot of nice impact cases. So you can think of the data from smart fridges, from your watch, from your wearables, etc., etc. Healthcare has been one of the most important impact cases. Several companies have become unicorns by working in this space with data and collaborative analytics. Sorry, I need a minute. Great. So let's go. We have, what's the framework? We have a bunch of agents. That's how we call the different stakeholders in game theory. You know, they are agents, and they're in a game together. We have a central agent. You have different scenarios I'm going to discuss, but in all cases, we have a central agent. The central agent has a task, an analytics task. For us, it's regression for forecasting, it's learning for forecasting, but it could be clustering, it could be classification, it could be reinforcement learning, you name it. And in all cases, this central agent may need or may want some help for some support agents that have data of relevance, okay? Here we consider the case where they could go to an analytics platform, the central agents, they pose their task, and then they try to find people that can help them, other agents, the support agents. So we have three scenarios here: collaborative analytics, data markets, analytics markets. In the three different cases, it's just different ways to think of the interaction between agents. You see at the bottom, there can be interaction in terms of computing, in terms of exchanging data, in terms of payments, all right? So let's go through them one by one. Collaborative analytics, it's for instance the first paper I published here at this conference 10 years ago. We were just saying they're just going to collaborate. It's completely altruistic. We do distributed learning, we do federated learning, and we get the support agents to help the central agent through some iteration, through some distributed computation, without ever sharing the data, right? You can have an encryption layer, etc. The problem is that since it's being purely altruistic, maybe some agents say, I don't have the incentive to do it, right? The incentive in principle is that we take turn. So you help me, I help you in the future. I have to say in practice, it's not very easy to make it work. The other idea would be data markets. If data is a commodity, why don't we just have data exchange platforms? And I think you have that in China, we've been trying that in Europe. We want to have data platform, data markets. It's very difficult to price data. So as much as it's a great idea, pricing data is a very complicated endeavor. So yes, we want to go in this direction, but there's a lot more work to be done. So maybe something that's easier to handle, and that I will dig into afterwards, is to have this kind of analytics markets. So in analytics markets, we just agree on the kind of tasks we want to handle. We agree on the way the agents are going to interact, and there's going to be payments for distributed computation and for data sharing. Okay? So that's the three scenarios that we want to consider. If you were to think of a supervised learning setup, we most often use supervised learning, right? When we want to learn for forecasting. So if you use a supervised learning setup, you could try to think of it as your design matrix X, right? Here, you have your design matrix X, you have your response vector Y, right? So it's the most simple setup you may consider with these features here and this response vector there. We could have a market for observations. So that means that the central agent has a bunch of rows to learn, to estimate their parameters, and maybe they want to buy more rows, right? So they want to have more values for input features and corresponding value for their target variable. But that could be a market for features. That's the market I'm going to dig into afterwards. So the central agent may have a bunch of features themselves, the target variable, but there are also features out there that exist that could be valuable that this central agent doesn't own, right? And so this central agent may want somehow to purchase or get some use of these extra features. Finally, and so that will be the talk by Shiwen that you should attend in the coming days, it could be labels. Think of it for all these autonomous cars, you know. They generate a lot of images on the road, for instance, but they need labels. They need to know, is there a pedestrian, is there a traffic light, is the traffic light red or green, etc. So for many tasks, you may generate a lot of input features, so you have lots of lines for these input features, but you need to have these labels. Maybe the autonomous driving is not the best example for you. You can think of it in terms of some pharmaceutical research. Whenever you generate samples, you're going to need to annotate these samples through some clinical lab procedures, and it's expensive, right? So you have all these inputs, but you need the labels. So which labels do you want to buy? Which are the most valuable to you? Okay? So we have lots, what I want to say here is that we have lots of different setups, and we've also worked on alternative ideas, being that we could do trading models, doing transfer learning. So if I want to warm start my model and do transfer learning or knowledge distillation, maybe I have to pay you for that, because you help me learn faster and better. Good. So there's no limit to your imagination if you want to design some kind of markets for analytics. I want to dig in a specific market that's called the regression market. I think that's the simplest setup that we could discuss here. So I think it's a nice example. And the way I want to do that, I'm going to use an energy example again. I hope you're happy with that. So we have the central agent. We're going to call it forecaster. And the central agent has a regression problem. And the central agents want to forecast renewable power generation, let's say it's wind power, at a certain site, right? So the target variable is wind power generation at this site. The central agent has a lot of features that can be their own weather forecast, their own measurements from the past for weather variables, for power variables, etc. And the central agent here, as of now, knows there are some support agent that exists with some relevant data, but they don't try to interact, okay? The central agent is on their own, they just do their best with their own data and features. So to keep it simple, we're going to say that the central agent set up a regression model that is linear in the parameters beta, right? So we have beta 0 plus a sum of beta I xit. That's a very simple linear regression model. You could generalize that to make it plan-based or polynomial basis, as long as it's linear in the parameters, we're good. All the theory I'm going to show afterwards still holds. So we have this model, we have this regression model. The central agent, obviously, in sample, is going to use a batch of data to fit this model. So we have an estimation problem, and by fitting the model, we want to learn these parameters beta. So we have n plus 1 here, you have the intercept and all the other betas for the linear model, and we minimize a loss function, right? So that can be a quadratic loss, that can be a pinball loss if you want to learn for a quantile, for predicting a quantile. But in all cases, we have this convex loss function that we want to minimize. When we've done the estimation, we have the parameters, so we have a beta hat, and we have the value of the loss function after fitting the model, right? So these are the two outcomes that we have. Parameters, by minimizing the loss function, and we have the value of the loss function at optimality. So please remember this notation. It's S small omega star. That's the value of the loss function when fitting the model only with the features of the central agent. Okay? Good. So that's the starting point. I told you now, this central agent is aware that there are some support agents that could help with some potentially relevant features. So what is this central agent going to do? The central agent forecaster is going to pose the task on a platform, a regression task on an analytics platform. This forecaster is going to declare willingness to pay. So the forecaster says, I'm ready to pay €1 per % improvement in my loss function and per data point provided, okay? So that's the game. I post my task and I tell about my willingness to pay as the central agent. These two support agents show up and they have some relevant features that they provide to the platform. We call them Z1 and Z2, and they want to be remunerated. Now we have an overall set of features which is based on the previous features from the central agent, plus the two new features from the support agent, right? So we have an augmented regression problem, let's say, because we have the previous features plus the new one, and we can do the same as before. We can use the same model, fit the model, and then this was the model from before, the linear regression based on the features of the central agent. But now we have this extra two terms that are based on the features of the two new support agents, which by the way are called good data and useful features. So we fit this model. As I told you, it could be something more complex, more advanced, as long as it's linear in the parameters we find. So think of a spline basis, polynomial basis, your favorite idea, and it still works. Good. When we fit this model, we again get a set of parameters. Since it's an augmented regression problem, I write beta plus. It's the same kind of parameters we had before, so related to the features of the central agent, plus parameters for the two new features from the support agent. We fit this model with the same loss function as before, so you still have this rho, that's a loss function. I use a quadratic loss here in the example, but after in the case study application, I use a quantile loss. So you can use any kind of convex loss that you want. Again, when I fit the model, what I get is a set of parameters that I can use afterward out of sample for forecasting, and I get the value of the loss function at optimality, right? And now it's S uppercase omega star, because it's for the larger set of features. We agree, if the features are valuable, the loss function value should be lower now than what it was before when I only used the features of the central agent, right? So we have this delta in the loss function, and if you think of it as a game, it's like the value of the ground coalition in a cooperative game. So by playing together, they generated this value, okay? And now we can say this value is going to be a basis for payment. Good. So how do we define revenue and payments in such a market? It's actually not complicated. As I told you, we can use cooperative game theory and apply directly some basic knowledge from game theory, plus some consideration related to the setup. I told you that this central agent had a willingness to pay. This willingness to pay is per percent improvement in the loss function and per data point provided. So this is the willingness to pay, it's here. We have the improvement in the loss function, that's the delta between the loss function at optimality when we only use the features of the central agent, and the loss function at optimality when we use also the features from the support agent, right? This data is the value of the ground coalition, and we have a willingness to pay for this improvement. And then big T is the number of data points provided for the batch learning, right? So if you think of it in terms of units, we have something that is money per percent improvement per data point multiplied by improvement by data point is money, right? So the central agent is making this payment. How do we share this money? Forecaster now has maybe given 1,000 RMB to the market, and the market has to distribute that among the two support agents. There's something, as I said, it's a cooperative game, so we have tools from cooperative game theory to decide how we share. We can use an allocation policy, so you can think of Shapley values. And Shapley values have become popular in forecasting, right? To try to do some kind of explanation for black box models, for instance. So it's a tool that's familiar to forecasters, and it's a tool that we use a lot in game theory and for this kind of market based on cooperative games. So the forecaster, or the central agent, is making this payment, and now I'm going to share this payment among the agents, and it's going to be shared based on this allocation policy that I have here. The basic property of this allocation policy is that the sum of this coefficient is equal to 1. So we exactly share the pot of money that is paid by the central agent, right? And we want also them to be positive, which can be a bit tricky in practice, so we can discuss it afterwards. Good, so we have a market. We have a market, we can get the central agent to post the task, support agents to come, help, we generate some revenue, we generate some value, and we know how to pay the agents. In terms of market properties, it is actually a very nice setup because we have very nice properties we want to have for such a market. It's budget balanced, so there's no money appearing or disappearing. We have symmetry or anonymity, so even if you reshuffle the agents, they are going to be treated the same. It's not because the agents come in different orders that they're going to get different payments, right? It's going to be consistent. We have a 0 element, so if someone doesn't show up with a feature or their feature is not valuable, they get paid 0. We have incentive compatibility, which is very important. That means that agents have an incentive to do their best. They will provide you with their best features and their best data because they know it's the only strategy to improve their revenue. And finally, we have also individual rationality. In principle, no agent is in a loss-making position. So if you enter this market, you're not going to lose money. In the worst case, you get 0. In the best case, you make money. Good. I showed you a case that was for batch learning. The thing is, in-sample batch learning is not very useful. I guess we all know that as forecasters, right? We fit a model in-sample on a batch of data, then we go out of sample. Personally, what I do is that I do online learning. So I don't want to use a batch, I want to learn on the fly based on data streams. Whatever we've been doing before, we can use it also for online learning and forecasting subsequently. So it's a very nice property. This is based on the fact that Shapley values are additive, linear and additive. So if we want to update Shapley values on the fly, we can do it the same way we update estimates in a model on the fly. So yeah, you can read the paper for the detail. And finally, which is even more interesting, when I do out-of-sample forecasting with this kind of idea, I can use SHAP or my Shapley values to also say genuinely in out-of-sample forecasting, I use data from others, my forecast can be better, I know how much payment and sharing of the payment we should have consequently. So all the ideas I showed you, we can use them for batch in-sample learning, for online learning, and for out-of-sample forecasting, right? So we have a very complete market that can be used generally. I want to show you some illustration through some simulation, just so that you have an understanding of how it works. So think of a very simple data generation process. We have this variable YT, that's my target variable, and the DGP is such that it's a linear combination of pass value for this target variable, so it's a first lag, a pass value for another feature x2, pass value for another feature x3, pass value for another feature x4, right? So this is a simple data generation process. We assume that one of the support agents owns the feature x2, that's here. One of the support agents owns x3 and x4, and so that means that the central agent owns this one, right? Good. This is the time varying parameters that I use. So you see these parameters beta 0, beta 1, beta 2, beta 3, beta 4. They vary with time. This is time here from 0 to 10,000. That's the number of time steps. And you see here the evolution of the different parameters. So you have beta 1 that says flat. You have beta 0 that decreases a little bit. That's the pink one. You have beta 3 that goes up and down, etc., etc. Right? So I just want to illustrate what's going to happen. First, the central agent here, A1, declares a willingness to pay of 0.1 euro per unit improvement in a quadratic loss and per data point. All right? Good. We do online learning for this DGP. I cheated a bit, I initialized to the values that were the correct values, so we're just tracking the parameters. And you see what's happening here. I told you there were 3 features. And so for each of the features, we want to have some instantaneous payment at every timestamp in the data set and update the parameters. I use the support agent features, and then I'm going to pay the support agent for the data they provided. So these are the instantaneous payments in euros. You see through time from 0 to 10,000, based on the I would say the amplitude of the parameter values. Different features have different value to the central agent, and so the payments change accordingly. So you see here, for instance, the feature x2 has this value increasing through time, so that they get paid more and more. x3 has this value increasing and decreasing, that reflects the shape of the parameter trajectory I showed before. And it's the same for x4. It's valuable, but then it gets less and less valuable over time. We can look at it in terms of cumulative payments. So if we were somehow to add this up, right, through time, this is the kind of cumulative payments that are given with these different features. Okay? So based on this idea, we have online learning, we have some payments that are appearing, and the agents are just piling money, if you want, right? Good. How does that happen with a more realistic case study? So that's really what I want to do now. I've been trying with some students at Imperial College, I've been trying to discuss it with some colleagues. How can we design some kind of platforms where we do it for real? There's a few platforms out there for prediction markets. There are not so many platforms for this kind of analytics markets. We've tried a few ideas. We've not converged yet, but I want to show you some kind of simulation that we've done for a bunch of wind farms in South Carolina. So this data is semi-real, if you want. It's data generated by colleagues in the US. You have the location of the wind farms here. You have the nominal capacity of the different wind farms. They are all within this radius here. It's 100, 150 kilometer. I think, yeah, around South Carolina. And you have these nine agents, and they're all in the market together. So they all take the role of being a central agent, so that means they're asking others to supply features, and they also all take the role of being a support agent, so they supply data to each other, okay? In all cases, we've set up a basic model. It's one step ahead forecasting, and we have a basic model where you have autoregressive model for the local data of the central agent, and then you have some lag values for the other features around. It's because we know for wind energy forecasting, there's some, let's say, diffusion of information, right? Depending on the movement of the weather systems, some of the wind farms, for instance, on the west, are going to serve as sensors for the wind farm on the east, all right? And then maybe the movement of the weather system change, and then it's the opposite, okay? So they will take turns, somehow having valuable information with each other, and the information is spreading through these lagged values. Good. So in principle, the market, and that's where it gets a bit complicated, the market also has to do some kind of feature selection, because obviously we only want to keep the valuable features, okay? So this is the basic model, but afterwards, we have the central market platform that is actually selected what are the support agents that are valuable to each other. Good, this is an example. So we do online quantile regression. This is the nominal level of the quantile I care about. So nominal level is tau equals 0.55. And we have these models I just mentioned with 2 lags for the central agent and 1 lag for the support agent. This central agent is just me who made it up. This central agent is willing to pay $0.2 in sample, so that means as they learn, they're going to pay for the value of using the data from others, and they're ready to pay $0.8 out of sample. Remember, it's per unit loss and per data point, okay? If you look at the specific case of A6, so when A6 is a central agent, A6 is paying others. A6, through the market platform, got this support agent selected, A1, A4, A5, A8. So if we were to look at the map, I'm sure it would make sense, and we would see on the map that these are the wind farms that are close by and carry some information when the weather systems are moving. And you see here the kind of payments. It's like for the simulations, except that here we use this realistic data. You see that over a period with 60,000 time steps, we have the payments that are building up for these different agents, A1, A4, A5, A8. We have 2 markets in parallel, because as I said, there's one market for learning, so here it's for the online learning, and we have one market for out-of-sample forecasting. So whenever we do forecast and we go to the market to bid, we actually use the data from the support agents and reward them for the fact they helped improving the loss function, out of sample. So we reward them both in sample and out of sample. How does that look like when we pull everything together? So when we pull everything together, you get this kind of plots, where here, again on the left, it's in sample when I do the learning. On the right, it's out of sample when I do the out of sample forecasting. The way to read these plots is that you have the agents here at the bottom, A1 to A9. The overall size of the bar is how much money they get overall, okay? So overall, agent A1 gets $25,000. Agent A2 gets $34,000. Agent A4 only gets $4,000, etc., etc. So you see there are huge variations in the revenue they generate by sharing their data. Why? Just because their data is not as valuable for all the other agents. So typically here, A4 has data that is not very valuable. This wind farm generates data that is not very valuable to others. A8, in contrast, generates data that is highly valuable to others. Okay? And we have this case both in sample and out of sample. Eventually we have to sum up the 2 revenues, because there's this revenues helping to improve the model and this revenue helping to improve forecast out of sample. And the cool thing we get is that we can give a price tag per data point. So eventually this agent A4, anytime they generated a data point, on average they got $0.4. That's the one that generated the least money. On the other side, you have A8. A8, whenever they generate a data point, the data point has a value of $3.26, right? So it's 8 times more, okay? Based on this, we can think about business cases, right? Whenever you generate data at some assets, so here it's a wind farm, but it would be some other kind of assets, we can actually value each and every data point. And then we could say, oh, cool, It's part of my business model. Now I generate data, I can also make money with this. So that's the idea I wanted to discuss with you today. We still have some time for discussion based on that. What I wanted to say with this simple example and hinting at other ideas we're working on, first is that I think these kind of ideas have a bright future, right? I think we will do more collaborative and market-based analytics. Energy is a no-brainer. We see a lot of interest in the energy space, in China, in Europe, in the US. So energy is a no-brainer as a high-impact case. I told you before, the pharmaceutical area is also a no-brainer. They're already doing it. Healthcare and pharmaceuticals, they're already doing it. Transportation would be a very good one, and then I'm sure you can find some other ideas that you can share with us at some other conference. In all cases, I showed you examples of different ways we want to organize the system. The challenge we have is we need to incentivize data sharing. Yes, we want to incentivize data sharing, but is it always about money? Would you all share data for money? Who would share data for money? Can you raise your hand? So I don't have many hands. Do you understand my question? Would you share data for money? Okay. Would you share data if you get money but you lose privacy? No. So now we have an issue. Sven at the back is like, no, I'm fine. I don't care. I just share data. So data incentives for sharing is not just about the money. We've been looking at ideas where we are trying to value this in terms of loss of privacy, or also where you try to minimize the potential privacy loss when you share data. When I say privacy, I talk about people like us, right? There's data we may or may not want to share because it's about our privacy. But if you think of companies, for companies it's not about their privacy, it's about their business secrets. It's about, potentially losing a competitive edge in a market, right? So there again, we've been writing some papers that are under review, where we integrate the data market in some other market, and the way data is priced is actually endogenous with the other market we're considering, right? If we don't do that, it will not make sense. So there are some very good people, for instance, at Yale, that have been looking at this kind of markets also, where you integrate different markets with externalities. It gets very complicated, but we need this methodological development. I think us forecasters, we have a unique opportunity because we are this interface between the analytics and methodological world and the practitioner. So we can develop the methods, but we can also talk with industry to convince them that we should try it. I've done that for 10 years. I've not convinced too many people. But I still have hope and have faith we're going to manage. Eventually, one of the things that is key is that the value of data and analytics is linked to downstream tasks. I think you know there's going to be quite a few sessions these days where we talk about prescriptive analytics, about value-oriented learning, etc. Here's a bit of the same. I decided myself here about the willingness to pay. And some people have actually attacked me when I was submitting papers. They were saying, yeah, but how do you estimate this, right? So you run simulation studies, or you say, I have a business expert that's going to say, yes, for me, the value of a data point, what I'm ready to pay is this. But in practice, you don't know. It depends on your decision task. I've been looking at decision tasks where the actual value you get from extra data point is so low that you don't care about having a market. It doesn't make sense. But there's some other application where the value of data points is very high. I talked about pharmaceutical trials, right? If you have labels for pharmaceutical trials, the value of each and every data point can be extremely high. So it depends a lot on case study, and it's also nice for us because we like to work on methods, but we also like to work with a lot of different case studies. So it's an ideal playground for us to play. Thank you very much, and if you have questions, I'd be happy to take them. Let's say dominating. You may have some very large parameter values, right? And you're right, it's the parameter value relatively to the others that makes this feature as a very high value, right? So it is intertwined. You cannot just say, it's because of the parameter, it's because of the data point. They come together in a way. I agree. Thanks. There's a question.
Here.
Oh, Tom.
Hey, a great talk, Pierre, as always. My question is regarding the features. So I think you mentioned an assumption that when you add a feature, that feature is like either good data or useful feature. But what happens if you have, say, you add a feature and that helps, and then you add another feature, then the first feature you added no longer help, or two good features, put them together, then they may make it worse.
Yeah.
So
very good
how
point.
do they work?
So I totally agree with what you say. So the first part of the answer is that it's a cooperative game, and in a cooperative game, that's the game, right? If you have two agents that are very valuable and they get good sharing of the pot, right? When a third agent comes, this third agent is more valuable than the other two have to accept they're gonna take a cut, right? So here it's a bit of the same. We cannot change that. Though, as you were saying, sometimes also they can, let's say, counteract each other. If you were to have correlated features, Shapley cannot deal with that, right? So now the Shapley values don't make sense, and the payment they get are not fair, they don't make sense because of these latent dependencies between features. So some people at MIT, for instance, propose some robust Shapley evaluation approach. We also propose, we have a paper under review where we propose another idea for doing that, because otherwise everything collapses. The market doesn't make sense. I agree with you. Thanks a lot.
Okay. Thanks, Pierre. Wonderful talk, as always. In the sort of theoretical framing, the market looked like it was a monopsony. There was only one central agent buying the data.
Yeah.
And that's where this FI that is chosen makes sense, because they're going to be a price maker. Is the way forward something that looks a lot more like your application, which is that there's a competitive market on both sides of the market? And in that case, is there no longer, I mean, the setup then is no longer that you have this FI, but that there is a price for the data that is determined by what the buyers of the data do.
So very, very good point. So it's true. Here it's there's a single buyer, multiple seller setup, right? Eventually we want multiple buyer, multiple seller setup. In many cases, though, you can run these things in parallel. So if you think the buyers don't mind and the sellers are not exclusive, it's fine to split the market and make markets in parallel with a single buyer, multiple sellers, right? But now, if I spice it up and I say I want exclusivity, so whenever someone buys a feature, I say the feature is only valuable to me because I'm the only one to get it. The others don't get it, right? Then we have this issue that you mentioned. We can write it as a resource allocation problem where we know how to decide on how we share and how to do the pricing. And yes, you're right, then we won't use Shapley value anymore. We'll use the tension between the buyers and the seller to decide on how we have the prices optimally. Thank you.
Okay, just a quick question. So can we consider situations that you have agents in and out, randomly coming out and in agents?
Okay, so that's a very, very good question. We're working on that now.
So that's a follow-up question is that, will that be a situation in the end of the day, there will be a data monopoly? Some agents will host like, I have most valuable data and came into this market, have big value, so other agents could have no chance to come into, because you think those are, they have like garbage information from that data at the moment, you don't know in the future.
No, so to answer your first question, what's actually very nice there is there's been a lot of good literature on learning and forecasting with missing data. And so here, having a setup where you have agents that come in and out, you can actually treat it as a case with missing data, right? So you could have missing data at random, or you could have patterns for how the people come in and out of the market. So it's technical, it's complicated, but we know how to do it. What you were saying afterwards, I mean, I would say it's just a general issue, right? Whenever you set a market, if you have some agents that can easily get a dominant position, the problem is not due to the markets, it's due to the ecosystem there, right? So if you look at the energy application, there, the assets, it's all these agents that have distributed assets, wind farms, etc. Physically, naturally, they share somehow the ecosystem. There may be other applications where it's not that obvious, but I think it's more of a matter of regulation and policy, right? The same way today we have giants when it comes to data. Whenever you have a market set up in the future, some may want to regulate to say we don't want also giants to just control most of the data, because otherwise, again, these markets don't make sense.
I just had a question. The structure that you have is based on a willingness to pay per data point.
Yep.
I'm just wondering, is there any drawback to that structure? I could imagine as the central agent, I basically want to see the improvement in my loss function. And if
Yeah.
it takes you one data point or it takes you 1,000,000 data points,
Yeah.
why would I care?
Okay, so maybe I went a bit quick there. The main reason I do that is that eventually, whenever I use this market, it's in an online learning setup. So in an online learning setup, I move to my new time step. There's a new data point to come. I make my updates, and then I assess the value, I define revenue and payment, and I move on. So I have to make it volumetric in that sense, because every time I move, I have this one data point that comes in, right? So that's why it's per data point, because it's sort of in an online setup. After, if we do batch, you're right, when I answered earlier with the lasso, we did it also the same way. We say, if we're in a batch setup, actually more generally, I don't care about the number of data points. It's just about quality. But if you go online, you have to have this volumetric thing to incentivize receiving the next data point every time you want to make an update. So that's why it's been done this way.
Got it. Thank you.
I think we have 1 minute left. So maybe it's the last question, maybe?
Thank you very much. Very
Thank you.
interesting. I just wondered, because there is a lot of estimation error here. Because when you evaluate the return, you might have a very, very inefficient estimate.
Yeah.
And so the actual value of the new feature
Yeah.
is...
Okay, beautiful question. So yes, this is, there's no theorem in this talk, but there are lots of theorems in the paper. And one of the issue we have here is all the nice results are in expectation. And then, as you say, on the fly, if we don't have so much data or the quality of the data is not very good, model is misspecified, it will actually affect the way we do the valuation. So we've been looking at properties in terms, so I mentioned individual rationality, that agents are not in a loss-making position. We know it's true in expectation, but if you have more complex setup like what you mentioned, then it's actually more difficult to prove. So then we have a bit more work to do on modeling and estimation so that we can guarantee these properties, right? So it's a very good point.
We started a bit late, so we could have one or more.
One more question.
Yeah, pretty good talk. Can you go back to the slides 11? You mentioned something like merging data sets from different sources, right? Not only
11.
the features, but also like the page 11. Yeah, the first case, did you merge the data sets from different sources?
Oh, here I was just looking at it conceptually, but yes, you're right. Here, when you think of your observation, so here this is an observation market, the central agent has all these rows, and then these rows maybe could be bought in the future, and there might be many different agents, right, that have these rows.
Yeah, just a pretty quick comment here, because when you're merging data sets from different sources, maybe sometimes the issue of the distribution shift will exist. So sometimes you need to filter the data sets first and then merge them together.
No, so I agree with you. There's a lot of technical issues. Even for the feature market, we're talking about the effect of magnitude of coefficient and so on. You need some kind of standardization approach if you want it to make sense, right? Because if you bring features that have a huge range, features that have a small range, etc., it doesn't make sense. So here you're right, whatever happens, you always have this kind of data engineering layer where you have to make sure that it makes sense before you move on to the data science and the market layer.
Yeah, that's actually what I'm talking. Thanks.
Cool, thanks very much.
All right.
谢谢.
So let's thank Pierre for his excellent talk.